Students are requested to drop down their names for attendance purpose. Students are requested to drop down their names for attendance purpose. We will be starting in a short while. Students can drop down their name for attendance purpose, then we will be starting in a while. Students can drop down their name for attendance purpose, then we will be starting in a while. Drop down your names for attendance purpose. So we'll start now. See, this is the session 11 of atomic structure, and most probably if you see that it is the last second last session of atomic structure itself, right? After this we will be doing some electronic configurations and our chapter will be over. So you are required to continually revise this particular chapter for a better purpose of understanding. So in atomic structure, we have covered discovery of fundamental particles. Atomic models have been covered, that is Thomson, Rutherford, Bohr's model, and today we will deal with the quantum mechanical model. Spectral studies are done, uncertainty principle are done, photoelectric effect we have studied, and electronic configuration we will be studying in the next class, right? That is the last topic of our particular chapter, that is atomic structure. So today we will be dealing with quantum mechanical model of an atom. Okay. So here if you see that de Broglie suggested that electron was associated with a wave also, right? Basically the matter was having a dual nature, that is the wave nature also and the particle nature also, right? So he stated that electron similarly, because it is a matter basically, it will also behave as a particle also, and it will also behave as a wave, right? And there were also experimental supports for the wave nature of electrons, like G.P. Thomson gave an experiment, right? And in the last session we have discussed that diffraction and interference were also shown by electrons. So these suggested that yes, that yes, electron is having a basically particle nature also and a wave nature also, right? Then uncertainty principle came. Heisenberg stated that the position of the electron and the momentum of the electron basically cannot be determined simultaneously, right? So these all things lead to the generation of quantum mechanical model of an atom, in which we started treating electrons as a wave, right? So concept of stationary orbits as suggested by Bohr, because Bohr suggested that electrons are revolving in the stationary orbit, had no more significance because he was not considering the wave nature of electron. He was only considering the particle nature of electron, right? So now we are studying the quantum mechanical model of the atom. Okay, so yeah, no issues, Arun. So the quantum mechanical model of an atom now deals with or treats electrons as wave, right? So according to uncertainty principle, we have studied that what? That delta x dot delta p is greater than equal to h by 4 pi. That means basically what? That the uncertainty in position is there if you want to measure accurate momentum, and there is uncertainty in momentum if you want to measure accurate position, right? So quantum mechanical model of the atom stated that instead of talking that that electron is present in this particular point, we will talk about the probability concept, right? That electron may be present here, may be present here, may be present here. So we will be talking about the probability of presence of electron, right? According to which it is possible to state or predict the probability of locating an electron of a specific energy in a given region of space around the nucleus at a given time. So this leads to the orbital concept, right? Basically he stated that orbital is what? The probability of finding an electron, right? For example, let us take a nucleus here, right? So here let us say in this space the probability of finding an electron is more. So we make basically a boundary surface diagram here, right? We make a boundary surface diagram. What is a boundary surface diagram basically? Yeah, we make a boundary surface diagram. What is a basically boundary surface diagram? Actually, where the electron is present, you will shade that region, darker, right? The probability, if there is a probability of finding that electron in that particular space, you will shade that particular region darker. And where there is no probability of finding an electron, you will not shade that region at all, right? And if there is a minimal probability of finding an electron, then you will shade that region a lighter one, right? So with the help of a boundary surface diagrams, we can actually find out the shape of the orbitals, right? So we'll discuss the quantum mechanical model in detail. This was just the overview of the quantum mechanical model, right? So remember that in quantum mechanical model, we are not saying that electron should be present here. Rather, we are talking about the probability of finding an electron in that particular region. Now, quantum mechanical model, we know that various quantum shells are governed by the principal quantum number n, right? So, n was the principal quantum number which can have values 1, 2, 3, but it cannot have a value of 0. N cannot be 0, right? So, basically he stated that the quantum number n represents the shell, that is k, l, m, n shell and so on. That means n equals to 1, k shell, n equals to 2, l shell, n equals to 3, m shell and so on, right? Then he stated that each quantum shell consists of subshells which are characterized by the azimuthal quantum number, that is L. So we have already studied that what are the possible values of L. L can have a value of 0 to n minus 1, right? This we have done. So these subshells are named as S, P, D, F, G according to their L values, right? For example, L equals to 0, it is S orbital, L equals to P, it is, L equals to 1, it is P orbital, L equals to 2, it is D orbital, L equals to 3, it is F orbital and so on, right? So each subshell consists of orbitals which are characterized by the magnetic quantum number, right? So each subshell, if you see, that is the S, P, D, F will have orbitals inside which are given by the value of m, right? For example, we studied that in S there is only one orbital, then in P there are 3 orbitals, right? Having value of -1, 0 and +1 of m. Similarly, D was having 5 orbitals and F was having 7 orbitals, okay, according to the value of m, which can take up values of -L to +L. This all we have completed in the previous session. The total number of orbitals in a quantum shell is equal to n square. Now this is important. See here that n equals to 1 if you take, so n square value will be 1, right? And we know that n equals to 1 is only having a 1s orbital, that is a single orbital. Then n equals to 2 if you say, so n square will be equal to what? 4. So the total number of orbitals will be 4. That means what? 2s and 2p. Now we know that 2s is having a single orbital and 2p is having 3 orbitals, right? So the total number of orbitals for n equals to 2 will be what? 4. Similarly, for n equals to 3, if you say, n square will have a value of 9. That means a total of 9 orbitals are there. So for n equals to 3, you can write down 3s, 3p and 3d, right? So 3s will be having 1 orbital, 3p will be having 3 orbitals and 3d will be having 5 orbitals. So all in all, 5 plus 3 plus 1 will give you 9. So the total number of orbitals present in a given quantum shell is equal to what? N square. You can remember this formula. Okay. Now, it suggested that an orbital is a variedly shaped 3-dimensional region around the nucleus where the probability of finding electrons is maximum. So he stated that what is an orbital basically? It is the 3-dimensional region we are obtaining where the probability of finding electrons is maximum. Okay, so let us look at the features of the orbital. It represents both the particle and wave nature of an electron. So here Bohr was considering that the electron is having only a particle nature, right? But here in quantum mechanical model, the orbital possesses the feature that it represents both particle and wave nature of an electron, right? Second one is the probability of finding an electron in an orbital is more than 90%. Now this is important. See, 10% may be found outwards the orbital, but 90% of the times the electron is found inside an orbital, right? Now this one is also important, that an orbital can accommodate a maximum of 2 electrons with opposite or anti-parallel spins. This we have done in the previous session also, that in an orbital you can have only 2 electrons, one with the upward spin and one with the downward spin. That means one is in the clockwise direction and one is in the anti-clockwise direction, right? So a single orbital can only be filled with 2 electrons. So if you are making an orbital and filling it like this is also incorrect because they are having 2 opposite spins. If you are filling a particular orbital, let us say this, like this is also incorrect because it can have only 2 electrons. So these are the small things that you have to keep in mind while filling an orbital, that an orbital will have only 2 electrons with opposite spins, one upwards and one downwards, that is one clockwise and one anti-clockwise. Now, this is very important. See, actually the quantum mechanical model was explained on the basis of equation that is known as the Schrodinger equation. So, in short, if we write Schrodinger equation can be written in the form of H psi equals to E psi. H psi equals to E psi. Now, let us study that what are H and E. Basically, H is known as the Hamiltonian operator. H is known as the Hamiltonian operator. Hamiltonian operator. Psi is known as the wave function. Psi is known as the wave function. E is known as the energy. E is known as the energy, right? So, what is basically operator like for example, let us say that d by dx is a operator. It is a differential operator, right? And it is operating on a function that is x square. So, what value will it give? 2x. Similarly, here also H is a Hamiltonian operator and psi is a wave function which is giving a value of E into psi, where E is the energy and it is also known as the eigenvalue. It is also known as the eigenvalue. See, we don't need to go into deep of these things. We'll just have a interpretation of the Schrodinger wave equation and not the derivation particularly, right? That how did it came, that is not in the syllabus. So you just need to remember the two forms of the Schrodinger wave equation, and the interpretation that can be done from that particular Schrodinger equation is in our syllabus, right? So H psi equals to E psi, where H is a Hamiltonian operator, psi is a wave function, E is the energy which is also known as the eigenvalue, and psi we have already done that it is a wave function, right? So, for example, let us say that d by dx is a operator. Sorry. Similarly, Hamiltonian is also a operator. If x square is a function, similarly psi is also a function. Okay. I hope it is clear. Now, the wave nature of the electron is described by this particular Schrodinger equation, right? So, if we change basically, or if we put the value of Hamiltonian operator and rearrange this particular equation, that is this is the another form of, or the second form of Schrodinger wave equation. This is the second form of Schrodinger wave equation, that is basically what explains the wave nature of the electron. Okay, so here if you see, del square by del x square plus del square by del y square plus del square by del z square into psi, which is the wave function, plus 8 pi square me, where me is the mass of the electron, h is the Planck's constant, E is the total energy, right? So E is the basically total energy, that is, let us say, kinetic energy plus potential energy plus the energy of attraction between the nucleus and the electron plus the energy of repulsion between the nucleus and electron. All energy terms are involved in E, right? And V is specifically what? The potential energy term. V is what? The potential energy, right? So psi basically represents the amplitude of a wave. We have already discussed that what is the amplitude of a wave. Suppose let us say that this is a particular wave. So the height of the crest or the depth of the trough is known as what? The amplitude of the wave, right? So psi is the amplitude of the wave at a point which is having a coordinate x, y and z. E is the total energy, which is also okay, Arun is asking something. Yeah, you need to just remember the equation. You can just remember the equation, the two forms of equation. Okay. But we do not require to go into the derivation of that particular thing. Okay. V denotes the potential energy of the electron. So, see, when we solve this particular Schrodinger wave equation, we will obtain the shape of orbitals around the nucleus, right? So, solution to this particular equation will give you that what is basically the shape of s orbital, what is the shape of p orbital, what is the shape of d orbital. Okay, see, for example, if you see that what is the equation of circle, that is x square plus y square equals to a square, right? Have you done it in your maths class? The equation of circle, the equation of parabola, have you done it before? Have you done that before? Equation of circle, equation of parabola. No, you will not get problems based on this formula. You will not get problems based on this formula. Rather, we just have an interpretation part. We will do some questions that can be asked from that particular thing, right? But directly on the formula based questions will not be asked in the examination itself. Okay, you haven't done that before. See here, the geometries, for example, let us say a circle can be represented by an equation. Similarly, a parabola can be represented by an equation, right? So, let us say that the equation of the circle is what? X square plus y square equals to a square. This is the equation of a circle, right? So, if you put coordinates, for example, let us take x equals to 1, y equals to 0, x equals to 2, y equals to 3, right? So, different x and y values are plotted, so we obtain a circular shape here, right? By the different values of x, y and a, we can obtain a circular shape here. Similarly, if you see, for an ellipse, the equation is x square upon a square plus y square divided by b square equals to 1, right? So similarly, plotting for x and y and a and b with having different values, you can plot a ellipse here, right, with the help of the values. So similarly, in the parabolic equation, what is the equation for parabola? That is y square equals to 4ax, right? So keeping the values, different values of y, x, right? So a parabola will be obtained. Similar to that, we can say that if geometrical shapes can be obtained by using mathematical functions, or basically mathematical equations, from Schrodinger wave equation, we can also determine the shape of the orbitals, right? For example, we were knowing the equation of circle, let us say, right? And we have taken the or solved that particular equation, got different values, plotted that on a graph, and we obtained a circle, right? Similarly, here also, if you solve this particular Schrodinger equation, then you will, when you will solve it particularly, you will get the shape of the orbital. So this is the basic significance of Schrodinger wave equation. Have you understood? Let me know in the comment section box. Let me know in the comment section box. Is it clear? Are you getting my point? What I wanted to explain? Should I explain it again? Let me know in the comment section box. Okay. Other people than Dipashri? Have you got my point? Like from solutions of equation of circle or parabola, we are obtaining the circular geometry, we are obtaining the parabolic geometry. Similarly, by solving the Schrodinger wave equation, we can get the shape of the orbital. So this is the basic significance of Schrodinger wave equation. So this is a very important point and is a frequently asked question in examinations. Psi, if you see, it has no physical significance, right? It only represents the amplitude of the electron wave or boundary surface of an orbital, right? So psi is basically what? The amplitude. But the real meaning is of psi square, right? Psi square gives the probable electron density, or basically the probability of finding electrons in any region, right? So psi is not having any physical significance, rather psi square, if you see, it gives the probability of finding an electron in a particular region, right? So if psi square is coming out to be positive for a particular point, then yes, that particular point has the probability of finding an electron, right, of having an electron. But if psi square equals to 0 at a particular point, this means that no electron will be present here. So basically not psi, but psi square tells us that where the electron would be present and where the electron will not be present. Okay. Now see here that previously, if you see here, that the Schrodinger wave equation was present in the Cartesian coordinates, that is x, y and z, right? X, y and z. X axis, y axis, z axis are known as what? The Cartesian coordinates, right? So the Schrodinger equation was expressed in terms of the Cartesian coordinates. But if you see that this equation can also be represented in the polar coordinates. What are polar coordinates? R, theta and phi. R, theta and phi. So let me take a particular point here, let us say, right? Let me take a particular point. So R will be what? This length. This length will be R. Distance from the nucleus will be R. Okay, this length will be R. Now look at the video. See, if this is the point, let us say, so this will be theta. This particular thing will be theta, right? The angle which is made in this direction will be theta, and this will be phi. This angle will be phi. Okay, so this is R, this is theta, and this is phi. Okay, so these are the polar coordinates. What are the Cartesian coordinates? X, Y, Z, and what are the polar coordinates? R, theta, and phi, right? So what we do is that we change basically the Cartesian coordinates into the polar coordinates. That is, we change x, y, z into the form of r, theta and phi, and therefore the Schrodinger wave equation can also be written in terms of polar coordinates, right? For hydrogen like species, that is for one electron species, it can be solved precisely. But if you take it for multi-electron system, it is very tough to solve that particular equation. So for hydrogen like species, if you solve that polar form of the equation, you can get the shape of the orbitals very easily. Okay. So the solution of Schrodinger wave equation for the single electron hydrogen atom yields the wave function of an atomic orbital, that is psi. So now in the polar form, let us say, the polar form of the Schrodinger wave equation, in which the x, y, z were replaced by r, theta and phi, when you particularly found the answer or the solution to that particular equation, you will get the solution as psi in the terms of r, theta and phi. So psi you will get now in the terms of r, theta and phi, right? So this particular wave function of an electron can be divided into two parts now, that is radial part. This r is known as what? Radial part, and this theta phi is known as the angular part. This theta phi is known as what? The angular part. I hope I am clear till now. Am I clear till now? Is it clear? Okay, good. So next, if we move on to see, so Schrodinger equations involves the radial part and the angular part. So we will study, about the radial part more, and we will leave the angular part here only, right? So RR, what does RR means? That you are having a radial wave function in terms of R, right? For example, what do you write? Fx, right? That means you are having a function which is in terms of x. Similarly, here also you are having a radial wave function which is in terms of r, right? So RR is the radial wave function which shows the dependence of an orbital on the distance r of the electron from the nucleus. So this particular wave function will tell you that how far, to what radius is your electron present. Okay, to what radius your electron is present from the nucleus will be told by the radial wave function. So the radial wave function, you see, it depends upon the quantum numbers n and l, that is the principal quantum number and azimuthal quantum number. This is the basis for question. This particular fact is the basis for question, that radial wave function depends upon the quantum numbers n and l, that is the principal quantum number and the azimuthal quantum number. Now see, you don't have to be confused by seeing such equations. You don't have to learn these equations, right? This is just kept for showing that these are the certain values of our function or the radial wave function that were being obtained for different orbitals, right? For example, if you say R and L, it is the equation R and L, that means this will show what? Principal quantum number, this will show what? Azimuthal quantum number. So 10 means what? 1s. So radial wave function for 1s can be given by this equation, right? Radial wave function for 2s can be given by this particular equation. Radial wave function for 2p can be given by this particular equation. Similarly, theta depends upon what? L and m. Theta depends upon L and m. L is what? The azimuthal quantum number, m is what? The magnetic quantum number, right? So these are the different values for different orbitals for theta, right? And similarly for phi, if you see, so phi only depends upon m. Phi only depends upon the magnetic quantum number, right? So these are the various values that are obtained for phi, right? For various orbitals basically, right? I'm saying again and again that you do not need to remember these equations, just I'm showing that how that particular equation is solved and we obtain the radial wave function as solutions to that particular equations, right? So these are the various radial wave functions for different orbitals for 1s, 2s, 2p. Similarly, we are having for 3d also. Similarly, we are having for 4s, 4d, 5f. Okay. Yeah, so you must have watched the movie Chandramukhi, right? So the lady was warned again and again, right, to not to go to the upper floor of the house, right? But still she went and she got mad, right? So here the perspective of resemblance is that you do not need to go deep into that particular radial wave function that we have discussed earlier, right? Otherwise you will have the same condition of like her, right? So jokes apart, we will move on to the radial wave function equation solutions, right? So that particular graph was plotted, right? We obtained the equation of RR versus R, right? First we plotted a graph of RR versus R. See here, the equation we are getting here, R1s is given as this, right? For different orbitals, we are plotting the graph between R versus R, that how that particular radial wave function is changing when we change R. So when we change the value of R, right? So for 1s you are obtaining the graph like this. For 2s you are obtaining the graph like this. Now this is very important, right? See, for 1s you are obtaining a graph like this, it's okay. For 2s, if you see that here, if you see That means the radial wave function is becoming 0 here. That means it is a node here. What do you mean by node? That the probability of finding electron here is 0. Right? So you have to learn the definition of node, that what is particularly a node, where the probability of finding electron is 0. Okay. So first we plotted R versus R, right? And if you see for 1s and 2s, right, what does it state? See here that here at this point, what is happening? We are saying that R equals to 0, right? R is what basically? The distance of electron from the nucleus, right? The distance of electron from the nucleus is R, right? When I put R equals to 0, what does it mean? It means that we are talking about the nucleus itself, right? So it is saying that the maximum probability of finding an electron is in the nucleus. Can you see here that the graph states that for 1s, that the maximum probability of finding an electron for 1s orbital is in nucleus, and then it decreases further, right? So this is wrong. How can we have electrons in nucleus itself? So therefore we plotted radial probability density instead. Radial probability density instead, right? That is r square dr. We plotted this, right? And we again obtained this graph. Then we plotted r square versus r. Now the graph was correct. Can you see here that in this particular graph it is showing that when r equals to 0, that means when you are stating that we are taking nucleus here, the probability of finding electron is 0 here. Similarly for 2s, you can see here that probability of finding electron in the nucleus is 0, right? So these graphs are considered now. These graphs are plotted now, right? And where this particular graph touches the x-axis, basically there is a node. That means the probability of finding the electron at that particular point is 0, right? So you don't have to remember these particular graphs, okay? These particular graphs you don't need to remember. We'll just have an interpretation of these particular graphs, okay? Here if you see that the probability is good here, the peaks decide the probability of finding an electron. Here also probability is good, right? So maximum probability here is this. At this particular distance, there is a maximum probability of finding an electron in a 2s orbital. Similarly, for a 1s orbital, at this particular distance, at this particular value of r, you will find the maximum number of electrons, right? And what does the node suggest? Node suggests that the probability of finding electron at that particular point is 0. Have you got it? Got it? Any doubts? Any doubts with this particular concept? Okay, good. Now next, similarly we plotted the 3 graphs for 2p also. So here you can see that the probability of finding the electron in the nucleus itself is 0, right? Here also 0, here also 0, right? And as soon as you go away from a nucleus at this particular point, there is a maximum probability of finding electrons for a 2p orbital, okay? Now it is very important, this particular concept is the basis for questions, right, for various competitive examinations as well as your boards also, right? Sorry, your CBSE exams also, school exams. So here if you see, Schrodinger equation solutions gives the radial wave function. This we have already learned, right? So we will discuss about that there are particularly two types of nodes that we will study, right? One is the radial node, and the other one is the angular node, Now this thing you have to keep in mind that the previously plotted graphs, can you see here nodes? Only you plot radial node in the graphs. Only radial nodes are plotted in the graphs. You will not consider angular nodes while drawing the graphs. Okay, so this particular thing will be discussed in details in the coming slides. So for meanwhile, you can say that nodes are of two types, that is the radial node and the angular node, right? So radial nodes are spherical in nature. While angular nodes are a type of a plane. Right? So if you want to show a radial node, basically you will draw a circle, an empty circle, right? But if you want to show an angular node, you will draw a plane here, right? So the depiction of radial node and the angular node we'll be doing in the next slides. So for meanwhile, what are radial nodes? That radial nodes are the point where the probability of finding electron wave is 0. Okay, so number of radial nodes or spherical nodes are equal to n minus L minus 1, right? For example, let us take for 1s, if you say, what should be the number of nodes, radial nodes? It should be n equals to 1 for this. For s, L equals to what? 0. So 1 minus 0 minus 1, that will come out to be 0. That means 1s orbital is not having any node, right? So when you plot the graph for 1s orbital, can you see any node? No, right? There is no node here. So you will plot such a graph for 1s that there is no node here. Now next, let us say for 2s we are taking. So for 2s, n minus L minus 1. So for 2s, n equals to 2 and L equals to what? 0. So it will be what? 2 minus 0 minus 1. That will become out to be 1. That means the graph which we are plotting, or the 2s orbital, is basically having one radial node or one spherical node, right? So while you draw the graph of 2s orbital, you will see here that one node is present, this particular node, right? Or if you want to plot the probability curve, basically, so here you can see node, one node is present. Similarly, for 2p, if you see 2p, number of radial nodes equals to n minus L minus 1. So n equals to what for 2p? 2. L equals to what for 2p? 1. So this will be 2 minus 1 minus 1, that will be equal to what? 0. Again, there are no radial nodes in 2p orbital. So as you can see that the graph is nowhere touching the x-axis. Okay. So this is how you can probably find out the number of radial nodes and plot the graph, right? You can just identify the graph by the number of radial nodes present in them, right? For example, if I tell you, let us say that two graphs are given, one is this and let us say one is this. So you have to identify that which one is the graph for 2s orbital. Now we know that 2s orbital is having how many number of nodes? One node, right? Here if you see there are 0 nodes, and here if you see there are 1 node. So this means this is the graph for the 2s orbital. So this is the basically scope of the questions from this particular thing. Okay. Now here if you see 2p is having no radial node, right? While 3p, if you see, for 3p, the number of nodes will be n minus L minus 1 radial nodes. So 3 minus 1 minus 1, that will give you 1. That means 3p orbital is having one node. Can you see here? The blue line depicts the 3p orbital. It is having one node here, right? So the peak of the curve, if you see here, the peak of the curve, this one, or this one, if you see, right, the corresponding R value of that peak of the curve is known as the most probable distance or most probable radius, basically. Most probable radius. That means maximum number of electrons in a 3p orbital will be found at this value of R, this value of radius, right? For example, let us say that it is 13, let us say, right? So at 13 atomic units, at 13 AU, basically what will happen in a 3p orbital at 13 AU, you will find out the max number of electrons. That means maximum number of electrons are present at the distance of 13. But here if you see for 2p, the maximum number of electrons are present, let us say, at 4, right? So this states that when you increase the quantum number, for example, when you increase the principal quantum number, that is for n equals to 2, we are going for n equals to 3. For 2p, n equals to 2, and for 3p, n equals to 3. For when we are increasing the principal quantum number, the distance from the nucleus also increases. The distance for the nucleus from the nucleus also increases, and this we have studied already, right? That this is the nucleus, so n equals to 1 will be this, 2 will be this, and 3 will be this, and similar fashion is shown by the graph also. Okay. So for 2p and 3p, if you see that 3p is the maximum number of electrons that are present in the 3p orbitals are far away than that of the 2p orbitals. Is it clear? The interpretation is very necessary. Is it clear to all? Are you facing some sort of doubt? You can let me know. Shall I move forward? Okay, good. Similarly, for 4s and 3d, if you see that 3d, the maximum number of electrons are present at this distance, right? And for 4s, the maximum number of electrons are present at this distance, right? And we are already drawing the principal quantum numbers, or basically the orbits as, or the shells as n equals to 1, n equals to 2, n equals to 3, n equals to 4, right? So as n increases, uh, the most probable distance where the electrons are having a maximum probability to be find out is the is increasing with the increasing quantum number, basically, right? So here also see for 3d, if you want to calculate the number of nodes, it will be n minus l minus 1. So these are the radial nodes, right? Angular nodes are not included in this formula. These are only the number of radial nodes. This is the formula for only the number of radial nodes. Okay, I'll explain it once again. See here. See, this is the most probable distance, the peak, the highest peak in the curve is known as the most probable distance, right? So what is the most probable distance? That is the distance at which you can find out maximum number of electrons from the nucleus, right? The distance from the nucleus at which you can find out the maximum number of electrons, right? So let us say that this particular value of R is 13, right? 13. So let us say for 3p orbital, at this distance maximum number of electrons are present, right? And for 2p, if you see, they are present at 4, let us say. So for 2p orbital, the maximum number of electrons are present here, right? And we already know what, that as we increase the principal quantum number, the distance of electron from the nucleus also increases, and the graph is also depicting the same, right? For n equals to 2, the electrons are present a little bit closer to that of the electron than that of n equals to 3. Is it clear now? Is it clear now, Arun? Is it clear? The peak of the curve shows that what is the distance at which maximum number of electrons are present, right? So we are seeing that as we increase the quantum number, the graph is also showing the same thing that we already know, that if you increase the quantum number, the distance of electron from the nucleus is also increasing. Is it clear now? Okay, good. So yeah, I was just explaining for 3D. So for 3D, the number of radial nodes will come out to be, principal quantum number is 3, L is what, basically 2 minus 1. So that will come out to be 0. So for 3D curve, can you see here that no node is present here. But for 4S, if you see, what are the number of radial nodes? 4 minus 0 minus 1, that is 3 nodes are there, right? So 1 node, 2 node and 3 nodes are present in the 4S curve. So remember that while you are plotting the graph, you are only showing the radial nodes and not the angular nodes. Okay, because here we are considering the radial wave function only. So you have to consider the radial nodes only. Now tell me the number of radial nodes in 5D, 5F and 6S. Come on, do it fast. Do it fast. Tell me the number of radial nodes in 5D, 5F and 6F. 6S. The formula that you have to use is n minus L minus 1, and L equals to 0, that means S orbital, L equals to 1, that means P orbital, L equals to 2, that means D orbital, L equals to 3, that means F orbital. Now solve it. What should be the number of radial or spherical nodes for 5D, 5F and 6F? These are the type of questions that you will be getting in your examinations frequently, okay? Comment down the answer. Comment down the answer and let me know. Okay, Arun is saying 215. What about Dipashri? So for 5D, if you see, it will be 5 minus 2 minus 1. That will be equal to 2. For 5F, if you see, it will be 5 minus 3 minus 1. That will be equal to 1. And for 6S, if you see, it will be 6 minus 0 minus 1. That will be equal to 5. So the answer is 215. Yeah, Arun, you are correct with your answer. Good. Dipashri, what about you? Have you got it? Okay, good. Dipashri, you are also correct with your answer, 215. How many radial nodes are there for 6D orbital? Calculate it fast. For 6D orbital, what are the number of radial nodes? For 6D orbital, what are the number of radial nodes? Okay, no issues. I'll wait for some time. I'll wait for your answer from now onwards. Okay, Arun and Dipashri are saying 3. So let us look at the answer. This one is n minus L minus 1. So that will be 6 minus 2 minus 1. That will be equal to what? 3, right? So for 6d orbital, there will be a total of 3 nodes. So how will you plot the graph? You can plot the graph like this. 1 node, 2 node, 3 node, and then you leave like this. Okay, so 1 node, 2 node, 3 node. So this is the probability versus R graph. Probability versus R graph. Okay, and if you want to okay, just leave it here only. This is the probability versus R graph, right? So accordingly, by finding out the number of radial nodes, you can find out the graph also, right? The nature of the graph also. Now see here that this we have already done, that particular wave equation can be solved in the terms of r, theta and phi also. So the wave function psi, it is known as what? Psi, right? So the wave function psi can be found out or can be expressed in terms of radial part also and the angular part also, right? So basically, if you see that the radial part depends upon the quantum number n and L, theta will depend upon L and M, and phi will depend upon M only. Okay, so this is also a scope of question that must be asked in the examination, that on which quantum numbers does the radial part depend, on which quantum number the angular part depends, and on which quantum number the phi parts depend. Okay, now next, see. Now, if you see here that if you find solution to the 1s orbital, right, that equation we have seen, that r equals to 2 minus something, that equation, right. So, if you see that for 1s orbital, the wave function psi was not having theta and phi, was not having theta and phi. This means what? That the s orbitals are symmetric. S orbitals are symmetric, right? And similarly, from the solution of the wave function for 2p orbital or the p orbital, basically, here if you see, these are the shape of orbitals that we are getting for px, py and pz, right? So they are same in the shape. Their shape is known as dumbbell shape. Their shape is known as what? Dumbbell shape. So these are these are same in the shape. For example, let us say that p orbitals are having, p subshell is having 3 orbitals, right? One having a value of -1, one is having a value of 0, and one is having value of +1, right? So basically it is what? Px, Py and Pz. So when you solved the wave equation for p orbital, you can get that these 3 orbitals, one of them is Px, one of them is Py and one of them is Pz. Shapes are the same, but the orientations are on different axes. While for the s orbital, if you solve the wave function, they were obtaining this s orbital are symmetrical, they are not directional, right? So Px, Py, Pz, they only differ in orientation, and these are degenerate orbitals. What are degenerate orbitals? That they are same in energy. The 3 orbitals of p subshell are same in energy. That means Px, Py, Pz will be having same energy, but their orientation is different. One is present on the, let us say, x axis, one is present on the y axis, and one is present on the z axis. Okay. Now, when you solve the equation for d orbital, let us say we are having a double dumbbell shape. Double dumbbell shape. So there are 5 orbitals for P, 5 orbitals for D, sorry, 5 orbitals for D, right? We draw as 1, 2, 3, 4, 5 depending upon the values of basically M. So this was 0, this was -1, -2, this was +1 and +2. So there are basically 5 orbitals in the D subshell. So one is what? dxy, sorry, one is what? dxy, one is dxz, one is dyz, right? One is dx square y square, one is dx square z square, and one is dy square z square, right? But these two orbitals are so similar in energy that these particular two orbitals combine and form a single orbital that is known as dz square. Okay, so what are the name of the orbitals, or what are basically the different orbitals of D? dxy, dyz, dxz, then dx square y square, and the rest two will form a single orbital because they are very much similar in energy. So they are forming what? dz square. They are forming dz square. Now look at the orientations basically. See, for dxy, if you see, draw x-axis and y-axis. Let us say this is x-axis, this is y-axis, right? So if we draw dxy, it will be present in between the axes. Can you see here? The lobes of the orbitals will be present in between the axes, like this, right? So positive, negative, positive, negative, right? The opposite lobes will be there, right? But here if you see, similarly also for dxz also, that means for dxz you will draw x-axis and z-axis and they will be present in between the axes. Similarly for dyz also, here plus, minus, minus, plus, okay. So similarly here for dyz also, you will draw y-axis, you will draw z-axis, then you will draw the orbital in between the axes. So if you see dxy, dxz and dyz are in between the axes, but if you see dx square y square, so it will be having along the axis. Dx square y square, it will be along the axis. So this will be like this. Can you see the difference? Along the axis. So this is the shape for dx square y square, or orientation of dx square y square. So this is the x-axis, this is the y-axis. Okay, am I clear? So this is the difference between dxy, dxz, dyz orientation and the dx square y square orientation. Now we are left with what? dz square, right? So this is very important. What is dz square basically? Here if you see that there is only a single lobe in dz square, right? In others we were seeing that opposite were present. For example, here plus, here minus, here plus, here minus, right? But here if you see that both the lobes are having positive charge and the negative charge, the negative phase, not charge, you call it phase. The negative phase is the ring present here, right? And dz square orbital is formed by dx square z square plus dy square z square. By the overlap of these two orbitals, we are getting a single orbital, that is dz square, which is having two positive phases and the negative phase is present as a ring here. Can you see? This is the negative phase. Okay, this is the negative phase. Similarly, for f orbital, see, till in examination till d orbitals you are asked the shapes and the orientations basically. For f orbital, because they are very complicated and it is very tedious to draw that particular f orbitals. Okay, so f orbitals are not asked in the exams, but you can learn the name of the orbitals, that is fy 3x square y square, fz x square y square, fyz square, fxz square, fxyz, fx x square minus 3y square, right? So f orbitals are highly diffused in shape. F orbitals are highly diffused in shape. F orbitals will not be asked in the exam, only till D orbitals you have to remember the shape and the orbital, shape and the orientation. And so F will be having how many orbitals? 1, 2, 3, 4, 5, 6 and 7, right? Relating to the M value that we were getting. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So this will be 0, minus 1, minus 2, minus 3, plus 1, plus 2, plus 3. These are the M values, right? So let us say for minus 3 it is this, for minus 2 it is this, for minus 1 this is, for 0 it is this, for plus 1 it is this, for plus 2 it is this, and for plus 3 it is this. So this is how you can particularly find out the shape of the orbitals using the Schrodinger wave equation solution. Okay, I hope I am clear. So is it clear till now? If it is clear, we will just wrap up the session for today. So that's all for today. Happy learning to all.